Hello, I'll be presenting on security comparisons and performance analyses of post-quantum signature algorithms. This project is cross-department with the Department of Computer Science and the Department of Physics and Energy Science. It is supported by the National Science Foundation and Colorado State Bill 18-086. Our group consists of Manohar, Simeon, Pranav, Yaroslav, Dr. Zhao, and Dr. Cheng, and this paper was accepted for publication into the ACNS 2021 conference. So what is a digital signature algorithm? Let's say you'd like to log into a banking website. Then you'll see the little lock icon next to the URL, and this is basically saying that a signature is being used to ensure the authenticity of the data being transmitted. A digital signature algorithm must have integrity, authenticity, and non-repudiation. Let's say that Alice would like to send a hello world message to Bob. Then a digital signature algorithm can be used to generate a public-private key pair. You would use the private key to sign the hello world message and generate a signature. Then the signature and hello world message will be sent over the internet to Bob. When Bob receives the message, he will use the public key to verify that the message is authentic using the signature, and because this is sent over the internet, the message can be tampered with, but this gives us a way to ensure that the message is cryptographically secured. The private key is only known by Alice because it grants the power to sign the message. The public key can be known by anyone since it can only be used to verify validity. The current signature standards are RSA and ECDSA. However, these are insecure against the quantum computer using Shor's algorithm. So back in 2016, NIST released a call for proposals asking people to submit quantum-resistant algorithms. And throughout the years, the submissions have been filtered down, and just recently, in July of this year, the Phase 1 of standardization began, and only 3 finalist algorithms were left standing: Dilithium, Falcon, and Rainbow. So if you look at the timeline, early 2022 will be the Phase 2 of standardization, where only 1 algorithm will remain, and this one will be standardized. The 3 finalists, Dilithium, Falcon, and Rainbow, are families of algorithms, so they each provide different security levels that optimize different parameters. Our problem statement is that as of right now, there is no easy way to compare between these algorithms to see which are optimal. If you want to secure an application from quantum computing, there's not a whole lot of insight about how to do it, which algorithms are more secure, which ones run faster, and so on. Since Dilithium and Falcon speak in qubits, and Rainbow speaks in quantum gates, this makes the task much more difficult. So our work fills these gaps by making security, performance, and size comparison visualizations. For our contributions, firstly we compare the size overheads with the security of each algorithm. The x-axis is the size consisting of public key and signature in bytes, and the y-axis quantifies the security of how difficult it is to break such an algorithm, where qubits are ran on a quantum computer and bits are ran on a classical computer. These plots compare Dilithium and Falcon, and these plots compare Rainbow and GEMSS using classical gates and quantum gates. So from these, we can see that Rainbow outperforms GEMSS in public keys because the size overhead is smaller, while the security in gates and quantum gates are both greater. So the goal in these plots is to minimize the x value, or bytes, and maximize the y value, which is the security. We perform a depth-width comparison across all algorithms as well, using the Universal Quantum Gate Model and Quantum Annealing Model. The DW cost is basically the total number of gate operations required to run each algorithm, and this is done because it combines all 3 finalist algorithms into a unit that can be compared. As you can see, Dilithium 2 has the lowest DW costs, followed by Falcon 512, and Rainbow VC Classic has the highest DW costs. We run a performance analysis on all the algorithms by varying the message length between 1 and 100 million bytes, or 100 megabytes. We take a new sample every power of 10, and as expected, we can see that the time it takes each algorithm to run increases as we increase the message size, but they also increase at different rates. So the next step was to link the points together by computing the equations for the lines of best fit. Then for the analysis, we found that in order to optimize the runtime, i.e. get the minimum of all the lines, is actually a conditional between 2 of the algorithms. We found that in order to optimize the performance, you should use Rainbow if the message length is greater than 387,578 bytes. Otherwise, for smaller messages, we recommend using Dilithium. As for our future research, we are currently implementing these digital signature schemes into QUIC and Bitcoin. QUIC is a transport layer networking protocol created by Google, and Bitcoin is the first and most popular cryptocurrency with a market capitalization of $200 billion. Despite the popularity, these two applications depend on signature schemes that are not quantum resistant. And as quantum computing becomes more feasible in everyday use, these applications will become more insecure. And that's why we're currently integrating these post-quantum signature algorithms into these applications to make them future-proof. We also had Pranav provide a demo of this research in action, which you can view in the link provided. If you'd like to discuss more, or if you have any questions, feel free to contact us through the emails provided or in the discussion below. We would love to hear from you. So that concludes our presentation. The ACNS 2021 conference will be held June 21st, 2021, so be on the lookout for our publication. And thanks for listening.